name is Claire Xiao, and this is Physics 2212 Lab 3, the magnetic field of a bar magnet. As an introduction to Lab 3, the purpose of this lab is to measure the distance dependence of the magnetic field due to a bar magnet, using the Biot-Savart law to create a computational model to visually represent the magnetic fields of the bar magnet for on-axis, perpendicular, and off-axis observation locations. Then we'll compare experimental values with values derived from the computational model. The results obtained, as you can see, the calculated value for distance dependence was n equals negative 3.115, while the theoretical value was n equals negative 3. And I have above on the screen the predicted value for magnetic fields 45 degrees off-axis and the observed value, which we'll dive a little bit deeper into later. Physics principle used, first, the magnitude of the magnetic field decreases as the observation location moves further away, and you can see the magnitude of the B bar equation shown. Understanding that the Earth produces a magnetic field, and then also the Biot-Savart law, which is the magnetic field of a dipole formula as listed above on the screen. So the experimental setup, so first we compensated for magnetic north. My phone was oriented to make the X component of the magnetometer 0. My location was 33.7490 north, 84.3880 west, with a negative magnetic field of 49. And then next was locating the chip. The bar magnet was oriented so that the axis was aligned east-west. Then I slid my phone along the line perpendicular to my meter stick until the absolute value of the X component was at a maximum and the Y component was at a minimum. Finally, my phone was rotated 90 degrees and then slid along the meter stick until the absolute value of the Y component was at a maximum and the X component was at a minimum. And you can see this in the figures below representing the steps that were taken. So this is the on-axis experiment. So when the magnetometer, I'm not sure if I'm pronouncing that right, is moved closer to the magnet, the X component of the magnetic field increases. When far away from the magnet, the X component of the magnetic field is near 0. And the observed values are shown below, which was the input to the Excel sheet that was attached to this lab. Next, for the experiment off-axis, the experimental B at 45 degrees was negative 8.3 times 10 to the negative 6, negative 2.389 times 10 to the negative 5 in the Y direction. And the observed values are shown below, again, from the Excel sheet that was included in this lab file. So next step would be calculating n using the equation shown. And as distance increases, magnetic field decreases. So this indicates that the slope is expected to be negative. As shown by the slope in the figure below, n is equal to negative 3.115, and below is the outputs from the Excel sheet that we were using previously before, and circled in red is the slope of negative 3.115. Next is calculating the magnetic moment, and you can see from my calculations that it ended up being 3.86889. So now diving a little bit deeper into the computational model, the first on the left is showing the magnet and magnetic field function. It was edited to create a function for the magnetic field, the defined function of dipole B with mu and r. Next is the B perp and B axis location and calculation that was inputted into the code as shown as the figure on the right. And then next, moving on to the computational model a little bit more, was the arrow visualization, which is shown by the figure on the left, and the B 45 degrees location and calculation shown by the figure on the right. And here's the output of the computational model. The blue arrows represent the perpendicular observation locations. The orange arrows represent the magnetic field at on-axis locations, and the magenta arrow represents off-axis location. And also I've attached the link to my GlowScript code. So observing the predicted results versus observed results for the B at 45 degrees. The predicted results are shown above and the experimental results are shown above, and using the percent error calculation, which is the absolute value of expected versus minus observed value divided by expected value times 100. The percent error is pretty large at 290.37%. However, looking at the percent error for n using the predicted results and observed results, the predicted results for n were -3 and the experimental results was -3.115, And using that percent error calculation again, the percent error was only 3.83%, which is pretty good. And finally, answering the report questions that were included in the lab report, first being, what if magnetic north was not compensated for? So the result of this would be that all the results would have been shifted by an equal magnitude. Therefore, the results of the graph that we saw earlier coming from the Excel sheet would remain the same. However, there would be a greater margin of error due to the larger difference between the predicted and the experimental values for the results. Next, answering the last report question, what if two identical magnets were used? The magnetic field would have doubled at each of the measured locations because the magnets are identical and oriented the same way. And the strength of magnetic field would increase because the number of magnets has also increased. Thank you for listening to my lab report.